Hello and welcome. My name is Sina Jawamardi.
And I'm Salman Bakhtiari.
We are both aeronautical students at Sharif University of Technology. It's a great honor for me and you. It's a great honor for me and my friend that to represent and manage the webinar for you. And in advance, I hope you enjoy this program. It's a great pleasure for us to have that we have a chance to perform an impressive presentation with Mr. Giulio Manzoni for the International Space. Hello, Mr. Manzoni. First, I want to invite Dr. Azad Kebriai, faculty member of Aerospace Department of Sharif University, who has significantly contributed to hold this program. Dr. Kebriai, you may now begin.
Hi everybody, good night and maybe good evening. Excuse me, since the connection may be interrupted due to low speed of my connection, my webcam is off. Dear Dr. Manzoni, audiences and the professors of Sharif University, you're welcome. And I'm happy to see you in the house of Aerospace Department for this webinar, and of course, unfortunately, virtually. As you know, today is the last day of the Global Week of the Space, and at our department, the student branch of the Scientific Association had different programs held in the previous days of this week. And now we are here for Dr. Manzoni's talk. First of all, I'm thankful to Dr. Manzoni for his acceptance of our invitation. And again, I'm sorry for change the talk time. Dr. Manzoni, as introduction, Dr. Manzoni, he founded the international company of Microspace, established in different countries, including Singapore, Italy, Austria, and the USA. And the title of Dr. Manzoni Tech is Nanosatellites from Space Technology Pioneers to Instruments of the Interplanetary Social Progress, the Experience, and the Contribution of Microspace, the company of Dr. Manzoni. Dr. Manzoni will speak for about 45 minutes, and then we have a time about 20 minutes for some questions. Again, especially I say welcome to professional faculties of our department, and because they are professionals on the topic of the talk, I'm thankful Dr. Esedi and Dr. Fati that they could help students for better management of end of the webinar. And as you see in the message pin, there is an online translation service, especially for undergraduate graduate students in my V class. Of course, myself prefer that you stay here and listen to Dr. Manzoni talk live and originally. We are ready that Dr. Manzoni begins this time.
Thank you, Dr.
Thank you.
That was great. Right now, my friend, Mr. Jawamardi, is going to give you a brief introduction of Dr. Manzoni.
Yeah, of course. The first, I want to start with this description. Giulio Manzoni, Doctor of Engineering, and who is an entrepreneur and inventor with the proven track record and over 25 years of industrial experience in developing products from conception, design, proof of concept, prototyping to production. Some of his notable products are pioneering non-satellites with parallel performances at a fraction of the cost of some of the most existing satellites.
He founded Microspace in Italy in 2002 starting developing micropropulsion systems for nanosatellites of 1 kilogram to microsatellites of 100-kilogram mass. Giulio opened Microspace also in Singapore in 2007 with a fully equipped laboratory for micropropulsion and satellite development and operation. Such micropropulsion systems have been fully qualified in the laboratory, have been installed on clients' nanosatellites, and have been demonstrated on a long-duration space mission by Microspace satellite PopSat HIB-1, launched in June 2014, fully operated by Microspace in Singapore from our own Earth station. Giulio, together with his small team of engineers in Singapore and Italy, has also developed an AthenOxSat-1, the second satellite of Microspace launched in December 2015. AthenOxSat-1 is now completing her 5th year of operation in space and has delivered thousands of interesting pictures to validate its new experimental imaging system and in-house developed attitude control systems and devices and algorithms. Mr. Manzoni will give you a lecture with the topic of nanosatellites, from space technology pioneers to instruments of interplanetary social progress, the experience and contribution of Microspace. Mr. Manzoni, I am more than happy to have you here, and you may begin.
Thank you. Let's see. Can you see me? Can you hear me?
Yes,
Hello?
you have your video and voice.
Is working. Okay. So I'm not sure how to run the presentation. The file
I may
that
run it for you, sir.
I'm sorry.
I do that for you.
We handled that.
Okay. So great, wonderful. Okay. Thank you very much. Thank you very much for this opportunity to be with you tonight, and it's a pleasure also. I think an honor to be able to close the World Space Week with this talk. And so you have already mentioned the title. I want to say that when I thought what should I give you as my talk, I thought yes, I want to give a description of our satellites, what we have done, but I want to put it in a wider context, which is how these satellites not only have performed as pioneering devices to demonstrate technology, space technology, but also how they are helping, and they will in the future possibly improve, create a social progress, and I will give you some ideas that probably are considered visionary. Now you may switch to the next slide, please. Yes, and so in this talk I will have basically 3 parts. First, I will describe the nanosatellites, then I will go through our application, and I will mention some other general application of this class of satellites, and then I will give you a concept, a vision that in which the satellite, this nanosatellite or nanospacecraft can be used for something that will allow mankind to reach space in a large number, and to build a new era of space exploration. So next slide, please. Yeah, just very quickly, Microspace. I began in 2002 with the seat in Italy first, and then in 2007 moved to Singapore. In 2014 and 2015, we launched our 2 satellites. So we have PopSat, which is in polar orbit, and AthenOxSat, which is in equatorial orbit. They are both cubesats. So they are in the class of nanosatellites, which means something that is between 1 kilo and 10 kilo mass. And then I also have a laboratory in Austria where I deal mostly with renewable energies and R&D and some special devices. while Italy is mostly dealing with industrial engineering and automation. And then we have, like I mentioned, a friendly collaboration with organization in US, which is called Asteroids, and you will see some of the material that we are doing with them in this presentation. Next slide, please.
Dr. Manzoni,
Yes.
Would you please speak a little slower? You know,
Okay.
students can't understand.
Are you doing translation at in parallel?
Yeah, we're doing that, but you know, students are happy to hear your own voice. So
Yes.
if you may speak a little slower. Thank you.
Okay, no problem. So far, is everything clear, or anything I have to repeat?
No, there is everything is okay. We can
Okay.
proceed.
Okay, thank you. So let's move to the next. So this slide shows two images from the beginning of our R&D work on micropropulsion. So the image that you see on the left is the microchip that contains a micro nozzle. And for your reference, it is a square of 5 millimeter times 5 millimeter. So it's something very, very small. And the size of the nozzle, you can already imagine inside this chip is even smaller. So we have a throat of the nozzle in the range of 10 to 100 micrometer. The image on the right is a computational fluid dynamics simulation, CFD simulation, of the flow that is exiting the nozzle. And this simulation was important and has been done in all the various possible configuration for this nozzle. It was important to verify that the flow was reaching supersonic speed in the nozzle, and it was properly transforming the pressure energy of the gas into speed and force, because the purpose of this device is to create a thrust, to create the force that is going to be used to produce attitude control and, if possible, formation flight or small orbital corrections for the nanosatellites. New slide. And here you see the real device, and you see two images. One is a scanning electron microscope picture of the nozzle looking from inside to outside. So there is a reference line that is, let me see, is 250 micrometer, to give you an idea of the size of the device. And then on the right side, you see is in comparison with the mosquito, with the small insect. Again, to give you an idea how small is this. This nozzle is able to produce 1 millinewton of force in the nominal configuration, and then this force can be adjusted continuously from 1 millinewton to basically 0, and in terms of duration can be controlled from a few milliseconds to an unlimited duration. And this is what we need to control the rotation of the satellite or to produce small forces that can change the position along the orbit. A new slide. So after several years of R&D, finally those nozzles were ready to be demonstrated in space. And we have been able to create a project to launch a satellite to demonstrate this micropropulsion system. Here you see the image of the satellite POPSAT that we developed starting in 2010, and we launched in 2014. And this is when the nanosatellite was ready to the launch. You see in the picture, there are some red arrows. Those red arrows indicate the position of the forces that are produced by the nozzle. So each arrow corresponds to one nozzle. And they are directed, of course, in various directions along the X, Y, Z, and also diagonal directions of the satellite in order to produce the torques that are possible to able to rotate the satellite, or net forces to move the satellite along the orbit. Then you see another SEM image, scanning electron microscope picture, where you can also see again the nozzle itself. And on the top right picture, you see when we were in Russia, in the launch base of Vyazny, to prepare the satellite for the mission, for the launch. In this particular picture, I am filling the argon propellant into the tank that is inside the satellite, so that this is the propellant used by the thrusters during the mission. And in the diagram, in the bottom right side of the slide, you see one of the many experiments we have done with these thrusters to rotate the satellite and to demonstrate that the nozzles are actually performing as expected. And you see in the there is on the horizontal axis the time in seconds, and then on the vertical axis you see the angular velocity as is measured by the gyroscopes of the satellite, and then the integration of the angular velocity in order to see which angle has been achieved. In particular, you see the red line is the angular velocity, which accelerates in one direction, stops, and decelerates in the opposite direction, so that you obtain a motion of the satellite. And the orange line shows the angle that has been rotated, which is in this particular case about is 2.7 radians. And we did many of these experiments during 9 months of operations, which was the planned time to use all the propellant on board of the satellite. Next slide, please. So POPSAT is our first mission, and then the second mission is ATENOXSAT. ATENOXSAT was required to do one very special experiment, which is to capture, to produce night images with the highest possible resolution in the smallest possible satellite. And because these are requested night images, then you will need to have a very high sensitivity. So we developed a special payload, a special optical miniaturized telescope with the largest possible aperture that you can fit in such small satellite. And this is the most important thing we developed for this mission. And if you go to the next slide, you can see some of the features and all the other subsystems that we have developed in-house. These two pictures have been taken in India at the launch base of Sriharikota, where we launched the satellite together with other 5 Singaporean satellites in equatorial orbit. And so, as I said, the most important thing is the optical payload that was able to achieve as requested 20-meter resolution on the ground. and taking images in the night. Other things that we developed for this satellite are, like in any case, also for the first satellite, the mechanical structure, and then in this case we developed the deployable solar panels with the double side solar cells. These satellites have to operate in the night, so we need to collect a lot of energy from the sun to store it in the batteries, so that it is used in the night, in the eclipse part of the orbit, to power all the subsystems. Another important device that we developed are the reaction wheels for the attitude control of the satellite. And then the control software, the algorithms that are able to aim the satellite with a high precision. Even we didn't mount any star tracker, just with the basic sun sensors, magnetometers, and gyroscope, we have been able to point this satellite to the target with precision better than 1 degree, which is enough in this case to target the camera payload, which is an aperture of about 2 degrees on the target. Also, we developed antennas, special antennas, and part of the electronics and the power system and several other subsystems of the satellite. The satellite has been launched in December 2015, and Atenoxat-1 is still in operation. And if you want, you can see on our website the frequency, and you can tune even with a very small portable radio. You can hear the signal of the satellite, and if you are able to process the signal that you receive, you can decode some basic information about the satellite health. And to the next slide, you can see some of the pictures. So not only we have developed this night vision high resolution payload, but we have equipped Atenoxat with 5 cameras in total. So 4 more cameras, 3 of them are fisheye cameras and 1 wide angle. So we can take a variety of different kind of pictures, even at the same time. And in this slide, you see on the bottom right, one night image of the city of Bangkok. And in particular, if you know where we are looking, you will recognize this is the airport area of Bangkok. Above that is a picture of somewhere in Indonesia. In this case, is taken with a wide-angle camera, and we see the clouds, we see the land and the sea. And on the left, the largest image in this case is the fisheye, one of the fisheye lenses took a picture. I think again it should be Indonesia if I'm not wrong. And you see the whole Earth visible by the satellite, which is about 5,000 kilometers in radius. In this case, we are at around 500 and something kilometer altitude, and it is on the equatorial orbit. So unfortunately, we cannot see many other interesting countries. The visibility is limited up to about 15-20 degrees latitude, north and south. A new slide. One interesting application is to detect the forest fires. You may know in Southeast Asia, forest fires are sometimes a big problem because they are done to clear the forest and to replace the forest with plantations. So this is destroying the forest, and not only is a problem for the forest, is also a problem for the countries that are then affected by the smoke that is polluting the air. So it's important to recognize as soon as possible when a forest fire is started, and we can see this from space. These are pictures we took with Asteroids, where we can clearly see the position of the starting of the forest fire, and this means we can alert the authorities to go there and possibly stop further ignition of other fires. Another slide. Can you switch to the next one? Thank you. Again, with the wide-angle camera, we have these kind of pictures where we can run automatic detection of the cloud shape. And you see in this case, there is a green profile that is overlay on the image. And so the software on board the satellite is able to detect the size and shape of the clouds. And if this information is given to the simulation algorithms of weather forecast, is a very accurate information to produce very accurate weather forecast. We can also, by taking multiple images, we can have three-dimensional images. We can measure the speed of the clouds. So this is all very important, very interesting information for meteorology. New slide. Another example of application, and this is with the main payload of the satellite, is security and surveillance. So this is a night picture of the strait between Singapore and Malaysia, and which is that black region that you see between the other north and south parts of the picture. And in this case, by properly using this image, we can see where are the ships and if they move in the correct direction or not. And even it is possible to detect if the loading, unloading, preparation of cargo, and the activity in the harbor and on the streets, so that if some of this activity is not legal or is not expected, it is possible again to alert the authorities and have somebody to check what is going on. So this is a very special and unique application. And at the moment, Asteroids is still the only CubeSat nanosatellite capable of such night vision, high-resolution images. And so we are very happy that we have this experiment in space, and this can also be used for future applications and in future satellites. So now let's move to the next slide. Here I want to present some of the trends that are today in the nanosatellite application. The easiest and maybe the first one that was available is the automatic identification system from ships or airplanes. Is sending some signals that normally are received by ground stations near the coast or harbor. But if the ship is in the middle of the ocean, then only a satellite can receive such information. And because you only need a radio receiver, not very complicated, a CubeSat, a small nanosatellite, can easily do this service. And there are several companies doing this. Another application that is coming of interest is the scanning of the RF radio frequency spectrum. Again, what is necessary on the satellite is some kind of receiver, a receiver capable to work at different frequencies, and with the correct antennas, it can check if the RF spectrum is used correctly or not, and if in certain region there is an unexpected signal produced, then it can alert for further action. A new interesting application is Internet of Things, and again, by using a small receiver and in certain cases a simple transmitter, it is possible to receive a small amount of data from remote devices that can be distributed on the ground, and the satellite can collect the information and then download it to the ground station, and vice versa, upload on the devices some new parameters for the control of very remote devices. Another interesting application is for weather data, to measure the GPS signals, so that by detecting how those signals are altered by the density, different density of the atmosphere, it is possible to obtain important data for weather forecast. And finally, Earth observation. This is a very large field with many different kind of application and several level of performance. So I didn't mention a small satellite like a CubeSat will never be able to have a resolution higher than, better than 3 or 4 meters from the lowest possible altitude. This is because of a diffraction limit of the optics, is a physics limitation. So if one wants to have a better resolution, needs to have a bigger satellite, basically. Of course, there are some advanced methods that may use multiple satellites together to combine the images and achieve a higher resolution, even if the satellites are very small. This may be something that will happen in the future, and that will need the use of micropropulsion to keep the correct distance and position between the satellites flying information. But in any case, most of these images are then used commercially, or they can be used for security or safety, solving safety issues. There are several reports that people can study to see how the market is growing. And so the small satellite market, according to a source that is cited here, is growing about 20% per year. So in the next 5 years, this is clearly a very big field where satellite will contribute somehow to the progress of society. And now, if we move to the next slide, I'll change a little bit the topic, because yes, we have wonderful technologies. We have these beautiful small satellites that are rather inexpensive. We can do many things, but we have to look at the world with the larger perspective and think what is happening. And unfortunately, I think we all recognize then there are several problems, and now we have to try to see what is the most important problem and if we can do something about it with our satellites. Next slide. So the essential motivation that I want to point out here starts from recognizing that the Earth is a closed system. What does it mean? So we receive energy from the sun, and we only have the material that is available on Earth. So nature has developed in millions of years a balanced cycle whereby the energy of the sun is used to run different long-term and short-term cycles, and then the energy is further released in the space by the Earth. So unfortunately, it is recognized very clearly recently that there is an impact of human activity on these cycles of nature, and we are consuming more than what the Earth can replenish. If we take the period of 1 year as a baseline, we are consuming about 1.7 times or more what the Earth can replenish, and which means that, for example, already in August we have consumed everything what the Earth can give us. And one of the consequences of this activity of humanity is that the temperature is rising. So the global warming is unfortunately a problem. You can go to the next slide. The next, please. So it's a problem. Global warming is a problem that is going to cause, unfortunately, already several natural disasters, but we expect very soon many glaciers in the Arctic, Antarctic to melt and to further raise the sea level. Next slide. So when the sea level is raising already at a small rate, we can possibly find solutions, but if, as it can happen, if the ice is melted too quickly, the solution not there, and several meters of raising the sea level will cause enormous floods and destruction of entire regions and displacement of several 100 million people. So this is a very serious problem that we think we should address as soon as possible. Next slide. So how do we address this problem? We observe that this problem happened because the size of anything is limited by the constraint of what is around it. So and the Earth is limited, has a limited size, so is a closed environment, and this means that there will be a tipping point where population will probably have big problems and suffer and will have a decline. On the other hand, if we are able to consider our environment in an open way, then we can still consider the growth to continue unlimited, and so for the population to be able to grow as is the natural trend. A new slide. And a possible solution is to open, we said we need to open our view, so we have to open to the volume of the Sol, the volume of the solar system. And this is a volume that contains a lot of material, and we can see the next slide. Yes. So in this representation, which is not done by me, you can find these images online. It's done by Mr. Alvaro Gracia Montoya. You see the several examples of asteroids. This is material we have is available in space, and it can be a small asteroid as small as a few meters, or it can be any other kind of size up to many hundreds of kilometers, almost 1,000 kilometers. And all this material is in space and it can be used. Next slide. So here we propose the new concept of using this material as construction material. So practically this become the new space stone age, which translates in astrolithic, is a new word. And I was presenting this concept in Vienna at the United Nations meeting for human space technologies almost 2 years ago. And you can find literature about this, and I am happy to send if you need to read these papers later on. Next slide. So how are we going to move to this new age? We start already, I mentioned, from the nano-satellite point of view. We have propulsion systems, we have optical devices, all packaged in very small satellites. And then the next step will be to create a demonstration mission where we show how we can collect a very large asteroid and bring this asteroid in the proximity of the Earth so that we can use the material. And the material will be used to create stations where people will be able to work and live. And with many stations in orbit, a large part of the population of Earth will be able to live in space, and we can relieve the Earth from the pressure of mining and destroying the nature. Next slide. So these space habitats will be produced by using the material from the asteroid, and we create some bubble, some cavity volumes where we can have a new environment similar to the one on the Earth, protected by radiation, and where people can live and work. Next slide. And the transportation from the ground to these bases will be done by means of space elevators. Now, this is a very interesting concept, not very popular, maybe because it is the material necessary to build a space elevator is not yet available. We need an extremely strong material, but the technology is progressing, and we are probably not very far from the availability that will allow to build a space elevator. Basically, is an elevator is a cable. Along this cable, you have a lift that is going up and down, and it can go all the way from the ground to the orbit where where is the station located. In this case, the geostationary orbit. Next slide. So all the transportation between Earth and the bases in geostationary orbit will be done both by means of space elevators and by the classic geo transfer orbit. And there will be definitely a LEO in low Earth orbit, a series of service stations. And then at the end of the space elevator, it's possible to launch spacecraft with almost no spending of energy, just using the excess of speed that is available at that point, so that travel to the moon and to Mars can start from there. Next slide. This is a slide to give an idea of how many people can live in a single bubble. And by taking a diameter of about 1 kilometer, you can see that you can easily have a nice environment for about 1,000 people per square kilometer density, which is less than many modern cities. So this will allow to have also sufficient green, areas and an entertainment area so that the quality of life will not be reduced even by being in space. Next slide. And by utilizing the material of the asteroid, the internal material, then it will be possible to create such bubbles, so that eventually there will be this cavity volume where you can be installed factories and housing and control systems, and everything will be protected by radiation. It will be filled with air, and it will be using energy coming from the sun as well. Next slide. So it is important to mention that this bases in space will be self-contained, like a small satellite is already a self-sufficient device. Also, these will be self-sufficient, so they will only receive energy from the sun and transform the material of the asteroid and the recycled material from the habitat into new product and new devices and components and everything necessary for life in space, and also something that can be sent back to Earth. Next slide. In fact, the return on investment of such a very big mission is an important element that needs to be considered. And precious materials are in the asteroids, so they will be sent to Earth and pay back for the initial cost of this complicated mission. Next slide. So how are we going to do this? We are going to focus the sun energy on the asteroid in order to vaporize it and produce thrust. Now I'm going to show you how it's going to be done. Next slide. This is more or less the same material that I presented at the United Nations a couple of years ago. Next slide. Next one. So we are going to redirect to geostationary orbit the asteroids by creating this thrust that is obtained by vaporization of the material itself of the asteroid. And in this picture, you see one example of an asteroid, and you see the trajectory with the red arrows that shows how we are going to control the force and to push the asteroid until it is parked in geostationary orbit around the Earth, where it will be used. Next slide. We need a lot of equipment, so the mission will start on a heavy launcher, and the most important part of the equipment that is going to perform the remote asteroid acquisition mission is a series of foils, very thin foils, that will made up a mirror, the mirror necessary to focus the energy of the sun. Next slide. And these mirrors will be rolled and will be full inside the launcher, and then it will be unfurled to extend and create the mirror surface. And I will have a video later to show how this works. Next slide. So we will use nano spacecraft based on our already demonstrated nano satellites to control the position of these mirrors. It is not only important to control the position, but also the curvature, so that the energy, sunlight, is properly focused in the correct point. and there will be many nano spacecraft in along these very large mirrors. The mirrors, you can imagine, it will be in the order of hundreds of meters to thousands of meters in size. So we need to control precisely the position in many points. Next slide. And now I'm showing again as a heritage, a precursors, the two satellites, POXSAT and Atenoxat. And there is in the middle of this slide an evolution of them, where we develop a reflect array antenna. This is an antenna for very long distance and high speed communication, because the whole mission will be controlled from the Earth, of course, and we need to have constant control of the activity of these satellites. So you see this antenna is able to focus the RF beam with a couple of degrees, so that most of the energy is utilized for the communication. And then there will be another kind of nano spacecraft with the thrusters, the propulsion system necessary for the control of the position of the mirrors. Next slide. So here I try to picture the whole idea. You see the asteroid, and you see the two set of mirror, one very small on the relatively small on the left of the asteroid, and one larger on the right. So it's a two mirror system to focus the energy of the sun and to produce vaporization of the asteroid material and the thrust. And then you see the other nano spacecraft that are maneuvering and imaging and relaying the information to Earth to receive also the controls from Earth how to properly position the mirrors. Next slide. So we want to understand how to use all these technology, very advanced technology, but possible technology for the benefit of mankind and for the Earth. And then we refer here to the Sustainable Development Goals. And the main principle is that this effort of collecting asteroid material should be directed to an equitable distribution. This means nobody should profit from it. It should be given to everybody. And if we apply this principle, then we can have abundance of material and new habitat for people, and we produce energy, and we can relocate the industry from the ground of the Earth to space, where it will not pollute the Earth. And technology, of course, will progress enormously, and there will be plenty of employment. So this is in line with many of the Sustainable Development Goals. And so we think this is a very meaningful activity to solve most of the problem on the Earth. Next slide. Okay, this is I want to mention again our principles and rules. So we recognize that the human expansion is unavoidable, is a trend that is always happening. So we have to learn how to live with it, and we take as a necessity that equality and fairness between all human beings is one of maybe our first principle, and then we want to also be sure that we respect the environment. And obviously, we only use feasible and available technology and known science. So this is not science fiction. This is all possible. We made all calculation and studies that demonstrate this is possible. And yeah, we don't want to create pollution, so there will be a mandatory recycling of all the matter. So only input allowed is the sun energy and the asteroid material. Next slide. This is the timeline for the whole beginning of the project. It's a very complicated slide. I'm not going to discuss it. Also, I think our time is almost finished. But you can find all this information on the website of the Asteroids, and I will have the links later on the last slide. And you can also always give you these references when you want to study that. Next slide. So it is also important that we recognize what are the scenarios that are in front of us. So if we can be pessimistic or we can be optimistic, and we can have a closed view or an open view. So if we are in the closed direction, then if we are pessimistic, we are surely facing a decline of mankind and destruction of the environment. If we are optimistic, we may believe that we are able to reduce consumption and stop the overpopulation, and to create a society where profit is not leading the desire and activities of people. But this is really optimistic, so I'm not sure if this is possible. On the other hand, in the open direction, if we are pessimistic, we have to be careful that opening to asteroid material utilization may lead to space colonialism, space wars. Of course, we don't want these things to happen. So again, we have to be optimistic, and this should be our choice, to understand that we should keep our view open to expand in the universe, but being careful and being optimistic with the right principles. This will be good for everybody and for nature. So now we move to the last slide. And so this is what I call the dawn of the astrolithic age. It is possible by using simple concept, complicated technologies, but everything is available and it can be done. And if you want to learn more, you see the website, the asteroids.org website. There is a little bit also on our website, on Microspace. And then I would like to give you the link to the video. Maybe you already found it. So I don't know how to type a link here. So let me see if I can do.
Mr. Manzoni, thank you for your great lecture.
Yes.
The attenders have asked a couple questions, which my friend Tina will read them out to you, and we will happy to hear your answers.
Yeah.
Sure. Okay.
Thank you. First, are there thrusters ion type or chemical type?
Can you repeat, please?
Yeah, of course. Are there thrusters ion type or chemical type?
Chemical.
Yeah.
The basic version is a cold gas.
Yeah, of course. And can you explain more about the technology and R&D process of developing micropropulsions?
The technology of the micropropulsion is so how to develop, you ask, right?
Yeah, how to develop, and explain more about the technology and R&D process.
Yeah. So this is a MEMS device. Is a micro machine nozzle, and is made on silicon, and is made by deep reactive ion etching. Now I'm going to show you a wafer. This is a wafer with many of these nozzles, and in order to produce this wafer, you need to start. You need to have a mask. So you need to do a lithography process, which is done by exposing the wafer prior you have to make a coating of resistive material, and then you expose the wafer under UV light through the mask so that you can project the pattern of the nozzle on the wafer. And then by selectively removing this resistive material, then you go into a deep reactive ion etching where the silicon will be removed only where it is exposed. And in this way, you can create the nozzle branches. And then by using a glass, second wafer of glass, they are put together, the two wafer, and then they are bonded by anodic bonding. And eventually you need to dice and cut by a diamond saw, and you obtain all the small nozzles. So this is the technology process. In few words, it sounds very simple. Actually, it's the same process that is used in the electronic industry to create some very common devices, even gyroscopes and accelerometer that are inside our smartphones use a very similar technology. But to optimize the size and the shape of the nozzles, it takes a lot of time, because the fluid dynamics of these very small channels is not obvious, is affected by turbulence and drag and viscosity and compressibility in a way that is a bit different from the very large rocket and usual nozzle. So that's why I needed to go through many simulations and manufacturing phases back and forth until I found the correct size to have the correct efficiency.
Yeah, that's right. Very great description. Thank you. Have you ever wanted or planned to use plasma thrusters, and which one of them do you prefer?
We have added to our coil gas thruster a system to ignite plasma, and I have some videos online. This is something I did some time ago. Eventually, this device is basically ready to go in space, but we haven't got the mission for that at the moment. And it is extremely difficult to do in such a small region to create plasma, but it's possible. And this is a different way than many other plasma thrusters, because other plasma thrusters that you can see around actually are quite bulky and quite large, and they will not be able to achieve their performance if they are extremely miniaturized. Our target is to make in the same small nozzle also a plasma thruster. So this is something very, very difficult, but eventually will give the highest possible efficiency to attitude control and formation flight.
Yeah, thank you. And is there any kind of threat which is seriously concerned with nano satellites? For example, potential debris colliding, external forces, and perturbations. What are the main solutions?
Yeah, so in fact you are totally right. It is a threat. It is a problem, and I think maybe exactly in this moment our satellite is going to pass about less than 100 meters from another satellite. We receive every week, every month, this information from the people that are the organization that is monitoring the space debris, and they tell us at that time of the next day or after 2 days you will have an encounter, and these two satellites will pass very near to each other, or maybe sometimes is a debris or is a old booster from a rocket or something. So it is a problem, especially in the polar orbit, which is very, very crowded. This kind of accident can happen anytime. Fortunately, at the moment, it didn't happen yet. But it is possible. And what is the solution? The solution is to remove as soon as possible a satellite when it is not necessary anymore from the orbit, or put it in a different orbit, and or also to have a propulsion system on board so that you can slightly change the orbit, the position. You know, if somebody tell you you have a probability of, I don't know, 0.1% to have a collision, then you can reduce the probability by 100 times just by moving your satellite 100 meters, and that costs very, very little. We can easily do it with our propulsion. Of course, this means you have to install a propulsion system on every satellite. And this takes a little bit of room, a little bit of power, a little bit of mass, and some cost. So the solution is that we have to do this for all satellites, especially the one in low Earth orbit, and then everything should be safe.
That's great. Thank you, Mr. Manzoni.
And I have a question from you, Mr. Manzoni. This is my own question. Which fields of engineering, which majors do you and your group work with, and what is the position of aerospace engineers in your group?
We don't specifically look at aerospace engineers. Of course, they are welcome, aerospace engineers, but we have mechanical engineers, we have material engineers, electronic engineers, physicists, and we have sometimes for some special part of the projects, people from mathematics faculty. So I think for us, the most important thing is to have an open mind to learn. We keep learning. I keep learning every time. Every new project, there is something new, and to be open to do different things. Of course, a good background of engineering is fundamental, and I think more or less any engineering school can give this background. If the person is smart and wishing to learn, will be successful.
Thank you. Now our professors from Aerospace Engineering Department will ask their questions.
Okay.
Yeah.
Hi there. Hi, Dr. Manzoni. I'm Nima Asadian, and thank you for your time and thank you for your presentation. I'm not sure the students meant me or the other professors, so I started to ask my questions. Again, thank you for your time. I enjoyed your presentation very much, and it was a lot of information and a lot of useful information for me and for the students. So thank you.
Yep.
I have several questions to ask, but I start with the first satellites. You were a part of that satellites, for example, PopSat or AutonoxSat-1, if I'm right. I was wondering if you can explain a little bit more about the mission. For example, if it does have any camera in the visible light range, because it has night mode vision, but I'm not sure if it does have any in the other range, or if it does have any other sensors, or how many pictures it can take at each orbit, and how it can send the pictures to the Earth, because probably the size of the pictures are very big, and what was the SWAT width, for example, because you told us about the resolution, but I'm not sure what's the size of each the width of the picture, and some things like that. If you can explain it about them, I appreciate that.
Yes, no problem. So Tenoxsat has 5 cameras in total. The first camera is the main payload, which is doing the night imaging in the visible spectrum. So it is a very sensitive sensor, and it is a very sensitive optics. And all the cameras are anyway in the visible range with a little bit of infrared, but it's not fundamental for us for this mission. The SWOT is for the night vision, if I'm not wrong, if I remember correctly, about 20 kilometers. So you have about 1,000 pixels, no? So it's a 20 meter becomes resolution, and 20 kilometer is the size of the picture. And then for the other cameras, you have 60 degrees aperture, which gives from this altitude about 600 kilometer SWAT, and in that case the resolution is around 300 meters. And then for the fisheye, the resolution is about 1 kilometer, and you see the whole Earth from the whole horizon, everything under the horizon. So is about at that altitude is a radius of 2,500 roughly, so 5,000 kilometers, the size of the image. And there are 3 cameras with fisheye and 1 wide angle and 1 high resolution night vision. So we have designed very carefully the integration of these 5 imaging payloads, because you can imagine the space is not very much on a 3U CubeSat. Is less than 5 kilo mass satellite, and it requires very careful management of the power. Now you ask me how many pictures per orbit. Basically, we can take a picture every second. So the problem is just like you say, how to get those pictures to the ground, and also how to store them. After you have downloaded the picture, you can always free the memory a little bit, and so it will be a way to be able to take more pictures. You have to understand this satellite was launched in 2015, which means it was built between 2013 2014 and designed based on available components at the time. So one of the biggest constraints was the radio, because in the UHF frequency, the bandwidth limits the amount of data you can receive, which means that to send a high resolution image, you need one pass, or 1 or 2 passes. Obviously, we don't always download high resolution images. Usually, first we download small clips, small compressed versions, and then when the image is interesting, then we download the complete image. And we have produced thousands of them. So you see some of them on the website, just to give you an idea. But there are really many images. Some interesting regions, especially the night pictures are interesting in the cities, on the coastlines, in the sea. We can see the ships. For the other wide angle and fisheye is interesting to see, like I presented examples before, the clouds, or the mountains and rivers, and the image can be processed to have an idea of the vegetation quality and so on.
Yeah, I'm sure they should be interesting pictures. I will check them for sure. Thank you. And okay, can you explain a little bit about the attitude control system? Because I observed that you have some also reaction wheels.
Yeah.
I guess the main actuator of the attitude control should be reaction wheels. And I was wondering how your micropropulsion system can help the attitude control. Is it used as a primary source, or is it going to be for desaturation of the reaction wheels or something?
No. So the two things in our view are used for different kind of missions. So PopSat was intending to be a short time mission. Short means a mission that can last between 1 month and 1 year. In this case, we don't have reaction wheels. So the attitude control is done only by thrusters. And this is a very special thing, and I think we are probably the first in the world doing this on such a small satellite. And why it is necessary? Because in that kind of mission, maybe you want to optimize the mass of the satellite, and reaction wheels are very heavy. And so in this case, our PopSat was about 3 kilo mass only for a 3U satellite, 3U CubeSat. And so we can use the thrusters both for attitude control and to for their even more interesting use, which is to enable formation flight. So on Athenoxat, on the other hand, we wanted a long-term mission. And because of the volume constraints, then we decided that the thrusters were not the solution. So in this case, reaction wheels are the solution. And we have 3 of them, like minimum necessary. And so we build the reaction wheels, and we have a control algorithm that is able to maneuver the satellite to swing the satellite from any position to the target, to the required target, in less than 1 minute. So what you do normally, you upload to the satellite the direction of the pointing and the time when it should start the pointing, and then the satellite will do the maneuvering. And if you are familiar a little bit with attitude control algorithms, of course you understand that first it's necessary to determine and estimate the attitude to know where is the satellite looking. And for that one, we have sun sensor, magnetometers, and gyroscopes. So we use a mix of deterministic and non-deterministic methods. So first, we combine the information from the sun sensors and the magnetometers to know the initial direction of the attitude, and then we can improve that by Kalman filters to include also the reading from the gyroscopes. And this is especially important when the satellite is on the eclipse mode, which means there is no sun available. So we need to fuse the reading of the gyroscope with the available magnetometers reading. Yeah, I also have to mention, obviously, both satellites have magnetorquers. If you are familiar with these devices, you know they are basically essential to stabilize. Oh, sorry, I have a cat.
No problem.
And so these magnetorquers are embedded in the solar panels, and they are interacting with the magnetic field of the Earth. And they can be used to slow down the angular rate of the satellite. This is especially important after deployment, after the satellite is ejected by the rocket. And then with that one, you achieve about 0.5 degree per second stability, which is good enough to start the other attitude control and the precision pointing.
Yeah, that's great. So they're used for detumbling and for desaturation of the reaction wheels.
Desaturation.
Other next step, of course.
We don't. The wheels are not really running constantly. They are running only when necessary. So we never go into saturation.
Okay. And for the PopSat, the only attitude control actuator is the thrusters. And can you tell us how much is the total impulse of the thruster? Because you said it's cold gas, so the total impulse should not be very much.
Yeah, sorry, this number at the moment I don't have in my mind.
Okay. No. Okay.
In the papers we presented at the conference, at the SmallSat conference. So I can send you the paper later so you can see more data.
But it lasts for 1 year in
Yeah.
operation for attitude control of the cubesat.
Again, like any other satellite of this kind, you don't do attitude control every time. So you do it only when you need it. And
that's great.
We were able to manage the propellant and the mission so that we last about 1 year.
Okay, I have one more questions, and regarding the mirrors at the end of your presentation,
yes,
because it was interesting for me. At first, I was wondering how do you manage to vaporize the materials, and the idea of using mirrors was brilliant because I was wondering if you need electric power to vaporize the material. So what I'm going to ask you is if the mirror is in orbit around the asteroid, or is it going to be installed on the surface of the asteroid? And if it's orbiting, because I guess it should move along all the trajectory from the, for example, main belt, or where the asteroid is, to near the Earth. So it should move around the Earth, around the asteroid all the time.
Yeah. The mirror, it should move around the asteroid all the time. But we have a way to control the position of the mirror by using the propellant of the nanosatellites, of the spacecraft.
So how long does it take to go from
an asteroid from the one that are not very far? It could be 1 or 2 years.
The near Earth asteroid or the main belt asteroid? Do you have any target asteroid for that mission, or it's in the concept?
At the moment, it is not decided which one. This mission is in a study phase, so there are many asteroids that are possible candidates. They are the study that I did. I think was about 1.5 astronomical units distance from the sun. So for that particular case, we estimate 1 year to reach the Earth.
Okay, so it should be near the main belt. Okay, thank you very much. I enjoyed it, and it was a brilliant idea.
Thank you.
And good luck. And again, thank you for your time.
Thank you.
Mr. Manzoni, another question has come up, and Sina will ask it from you.
Yeah, if it is possible for you. Mr. Manzoni, how do you see the market of the CubeSats?
The market of the CubeSat is, I don't think, is a terribly big market. Is an interesting market. Is good for demonstration missions. Eventually, I think what will be necessary. Well, by the way, what do we mean by CubeSat? That is also need to be clarified. The most popular size is the 3U, which is what we did. But somebody called CubeSat even 27U. Now 27U is becoming almost a microsatellite. And then when you talk about that kind of satellite, my question is: do we really need to have it in the form of a cube, or do we want to optimize to something that is better suitable for the mission? Because one reason CubeSat were introduced is to facilitate the way they are installed on the rocket, so that you have a very clear interface, very simple paperwork, and so the cube is the best thing, and then you have a deployment system. But then, even in our case, to deploy a 3-kilo satellite, then you still carry a 2-kilo deployer in space, so it's a big waste. And then if you are going to increase the size of the spacecraft to 27U or something like that, then how many kilo you have to waste just for deploying? This means that maybe you don't need anymore such kind of deployment system. And so maybe you don't need anymore the cube. And also the effort to design a microsatellite can be spent to optimize the shape, and this means I think CubeSat still remain a very interesting entry-level satellite, but when you go to more sophisticated mission, probably it may be different than a CubeSat.
Yeah, thank you.
Okay,
Yeah.
we can hear the audience's questions by raising their hand, and I think Dr. Fathi wants to say something. Dr. Fathi, we are hearing you.
Hello, Mr. Manzoni.
Hello.
I'm Fathi, faculty member of Aerospace Engineering Faculty, Sharif University. Thank you for your presentation. I have some questions. Do you explain about the launch process of your microsatellite at first? And second, if it is possible, please explain about the environmental tests done on your microsatellite. And third, how you finish the mission and end the mission of the satellite at end of the process. Thank you.
Yeah, thank you for the question. Yeah, so we launched our two satellites, one from Russia with the Dnepr rocket, and one from India with the PSLV rocket. And in both cases, we went to the launch base to do the final testing and calibrations and update of the software. And well, the launch itself is not something that you have much to worry, because the rocket company does everything for you. But you need to have some paperwork in place initially. And that paperwork, of course, is based on the environmental testing. So like you asked, environmental testing includes vibration and mostly thermal cycling. These are the two most important things. Vibrations are done on a shaker, which you may see we have some videos on internet on how we do that. It's a very standard procedure. You put the satellite in a testing box that is simulating how the satellite is held inside the deployer. So it's more or less like a deployer, but a bit stronger. And then the shaker is programmed to follow the profile of vibrations, accelerations that are required by the launcher. So you receive those information when you are dealing with the launching company. So the shaker will do the profile, and then will measure accelerations on the body of the spacecraft, of the satellite. And if those accelerations are within the required limit, then it's okay. If something is wrong, then it must be fixed. And usually is everything okay, because in the design of the satellite, we already took into account those vibration profiles to make sure that the frequencies, the model frequencies, and the amplitude of the vibrations are within limit. So all these procedure are done both on the engineering model and the flight model. So first, the engineering model is a prototype of the satellite, where is 80% equal to the flight model, more or less. And if there is any problem, there is still time to fix something, change the design, or improve some components. And then the flight model repeats the testing with the final values, which are not as high because the design has been already qualified by the engineering model. This is all standard procedure that is done usually for every satellite. There is a possibility to make simple procedure to do only qualification flight model, but we choose not to do that. We always do one engineering and one flight model. And then for the end of life, Well, actually, when these satellites have been designed and ordered, then it was not required to have any specific end of life. So basically, they are still alive and still in space, and they can still be used, and we can still contact them. So they will naturally re-enter the atmosphere after about 20 years, 20 to 25 years, and they will burn in the atmosphere. So this is one of the basic benefit of being in the lower orbit, in the lowest part of the lower orbit, so that eventually in the long term we don't leave rubbish in space. They will just decay and burn.
Thank you for the explanation. And another question: how much was the cost of your manufacturing the microsatellites?
Well, about cost, I think we should not talk. This is more a commercial topic, so I think you can find online several companies selling components. So you may guess how much is the cost of a satellite.
Thank you. Thank you.
We will hear our audience's questions, the students' question. If you raise your hand, and please
Ask your questions in English.
and before any questions, I want to inform you that you can give your feedbacks about this event held by the Science Society of Aerospace Engineers of Sharif University of Technology with the link posted below. We will happy to read your feedbacks and reviews. So, and Mr. Giulio, if you also give your feedback about this event, we will be more than happy to read and perform it on our next events.
Yeah.
So, any other questions? Please raise your hands
And ask a question, please. Yeah. And if it is possible for you, ask your question in English
only.
Yeah, only. We're waiting for your questions. Yeah.
Mr. Mahdavi.
Can you hear my voice? Can you hear my voice?
Yes.
Hello, Mr. Manzoni. I thank you for your presence in the webinar. I can see your product in cubesatshop.com, the Microspace MEMS-based micropropulsion system, and there is something weird to me here. The maximum required power is about 2 watts. I think it's very low to proportional to another micropropulsion systems. My question is, how do you deliver these voltage and the power requirement? Thank you.
Okay, that one is a cold gas system. So actually, you don't need much power. You need only to control the valves and to have a microcontroller that is doing the job. So 2 watt is the peak power. Actually, in the standby, for most of the time, it will consume only half a watt.
From Mr. Amirza Asari.
Yeah. Mr. Asari can speak.
Did you hear?
No, unfortunately, we can't hear.
I repeat. So
Yeah.
okay.
Thank you for explaining. In your website, this is a project that's named maybe hydroactive set.
No, I don't understand. What?
And there's a project on your website named maybe if I don't make mistake, hydroactive set.
Okay. Some of these things I cannot disclose. They are still in progress.
Okay, thanks.
Any other question? Sometimes we have intern, yes. Sometimes after they do a little part of the project, they remain with us. Yeah, not always, but sometimes.
Okay. Thank you, Mr. Manzoni. And because of lack of time, our friends to ask another question. And if you have any other point or any other thing to say, we would like to hear your voice.
It is. I just want to say it was a pleasure to give this talk. Something from for this opportunity.
We will be more than happy to keep cooperating with you and keep in touch. Thank you, and thank everyone for your attendance. Please don't forget to leave your feedbacks.
Yeah, we would love to have your feedback and read them, and to continue and keep in touch with Mr. Manzoni. And also, just it is not possible for us to answer another question, but somehow I would love to just answer another question for one of our friends, if it is possible for you, Mr. Manzoni.
Do you have enough time?
Yeah.
For another question?
Go ahead.
Thank you. All right.
Mr. Rosali?
Mr. Rosali?
Yes. Do you want to ask another question? Okay. Yes. We build the complete bus of the satellite. We have our own software, and we buy radios and batteries like most of the people, because that is such a standard thing already. So yeah, kind of 50-50.
That means you use other company subsystems such as Asteroids or some others, nano-satellite or cubesat provider, OVC communication systems, and other subsystems such as a power distribution system. Am I right?
Some part, yes.
Thank you very much. We will be in touch via email or other ways of communication for further discussion. We have some production in field of communication and CNDH in Sharif University. We are willing to provide these subsystems for you. We will be in touch by email or other ways of communication. Thank you very much for your time.
Okay.
It was a great honor for us and a greater experience for me, my friend, and of course other students.
Yeah, and that was one of the best presentations that I've ever seen in my life, and I would love to see you in next times. And have a good night.
Thank you.
Thank you. Have a good night.
Thank
Good
you.
Thank you.
night. Nice weekend. Oh, sorry.
Thank you.
Let's go.
Bye.
Bye.
Bye. You can leave now.
How to leave? You switch off. I don't know. Okay, maybe.